Hi everyone, and welcome to our next JenTalk, an overview of basic statistics. Let's start with the mean, median, and mode. Remember, mean is the average. So if you can calculate an average, you are doing statistics. The median is the midpoint. So if you have 9 data points, the 5th data point will be your midpoint. The mode is the most frequently occurring data point. The median and mode can give you some more information about a set of data than the mean can or than the average can, and oftentimes it's good to have all three. You may or may not choose to report all three, depending on if you learn a bit more out of the mean and out of the median and the mode, but it's good to know them as a researcher and then decide. We typically use the mean or average as we're reporting data, but sometimes that does not tell the full picture. So let's look at all three. Let's say you ask people how likely they are to use their new assistive technology software app on their mobile device. And 1 is the least likely, while 10 is the most likely. When we report findings, we rarely show the raw data numbers or all of their responses. Let's say in this example you asked 9 clients to respond and the mean or average was 4. From that, on a scale of 1 to 10 with a 4, you may decide that people are more likely to abandon the app than they are to keep using it based on the mean alone. Let's see if there's something more we need to consider. When the mean is not enough. However, if you look at the data and you learn that these were the 9 responses, might you think there's more going on than what you can tell from the mean or the average? Look at these responses. Of 9 people, you had 1, 1, 1, 1, 1, 5, 7, 9, and 10. So you've got responses ranging from the lowest to the highest. You have several of them that are the lowest, and some that are also pretty high. Now, if you'd asked a lot of other questions, you might get a sense for why some were very low and why some were very high. You might be able to find relationships between the people, maybe in their gender or their type of disability and whether or not they rated low or high. Maybe it's related to age, simply using mobile apps. Right now, though, we know that a lot of people ranked very, very low. Our average is a 4, which is low, and yet some people are likely to keep the app. So your median is 1, and your mode is 1, while your mean was 4. Your median is your midpoint, which is that 5th one. It's the 5th place. There are 4 on one side, 4 on the other. The midpoint is your median. Your mode, or most frequently value, is also 1. So 1s and 4s are standing out here. You can see abandonment is likely among many. Still, how did we get a 4 for the mean with all of those 1s? By looking beyond the mean or the average, we see outliers are present. In this case, we see that 30% of the clients expect to keep using the AT app. 30%, that's almost a third. Might that affect your next steps? Rather than abandoning the app that might get abandoned, maybe there's something else you need to understand. Maybe there's something you can do to change it to make it more appealing to the 1s in that 5. Or maybe you have 2 very different populations, and the population of people that like apps, maybe they're 18 to 28, with a specific kind of disability, well, that's a pretty large population and a population of people that's growing. Maybe you don't abandon that app. Maybe you just now know who you need to market it to. So beyond the 3 M's, or the mean, median, and mode, let's also talk about relationships and correlations. Let's look at slightly more sophisticated statistical tests. What if you want to know if variables are related with one another within your study? If you're collecting nominal data like sex, gender, ethnicity, political affiliation, things that are labels that are not numerically ranked, you might give male 1 and female a 2, but that's just to give them a label. It's not that male has the value of 1 and female has a greater value of 2, or Democrats, Republicans, Independents, and Green Party are 1, 2, 3, and 4, as if 1 represents less and 4 represents more, even if you might think that way. We all know that these are just labels that we attach to these categories. So you can't mathematically decide that if you have more women than men, that your overall population is a person that's slightly more female than male. These kind of nominal qualities don't work that way. They're just ways that we categorize things so that we can count them. So with nominal data, you still might want to see if there's a relationship between some of these variables. A relationship in the frequency of variables occurring together can tell us a bit about these variables and how they are interrelated. So in other words, are variables X and Y likely to occur or not together? Let's look at sexual orientation. We'll just look at heterosexual and homosexual for now, even though we know that there are many more than that. And let's look at it related to political party affiliation. Let's look at Republican, Democrat, Independent, and Green Party. None of these variables are numerical like age or income, as I mentioned before. They are categories that are assigned codes or numbers to represent each variable. Hence, they represent nominal data, the most basic, lowest level of data in terms of mathematical, statistical abilities. To test the relatedness between these two variables, sexual orientation and political party affiliation, you use the chi-square test. That's what you need to get from this. If you're trying to test to see if two nominal variables are related to one another, you're using a chi-square. The chi-square analysis relies on frequency data and therefore looks at nominal and sometimes ordinal level data. We can see if sexual orientation is more likely associated with a political party or not. But keep in mind, the result does not indicate cause and effect. So we probably would hypothesize that people who are homosexual are much more likely to also identify with being Democrats or maybe Green Party. And people who are heterosexual are probably widely spread among all the groups. I'm just guessing here, but those are the kind of hypotheses you would make. Then, after you made your hypothesis, you would use the chi-square after you completed a survey of your population. You have your sample, and you would see, are they really related, and is that relationship significant? Or are they, in fact, not related at all? And that's not a bad thing. Maybe your hypothesis is wrong, and you find out, you know what? Sexual orientation is not really significantly associated with any party at all, despite the notions that you may have had. So it's even interesting to find out when your hypothesis is incorrect. Sometimes it's even more interesting because it can dispel myths or biases that we have. Now let's talk about correlations. Let's say you want to know if things are correlated in a directional way. What is the relatedness of X to Y? Does X affect Y in a positive or negative way, or not at all? X is the independent variable, and Y is the dependent variable. Positive relationships and negative relationships refer to the direction of the relationship, not if the relationship is good or bad. Because directionality is being assessed, you can use ordinal, interval, or ratio level data. So the higher levels of data versus the nominal data. So already if you're doing correlations, you know. If you've only collected nominal data, you can't do a correlation. The best that you will be able to do is assess if there's a relationship through chi-square. But if you have ordinal, interval, or ratio level data, you can look to see if two things are positively or negatively correlated with one another. So let's look at an example of applying correlations. Let's say you want to know if an increased awareness of the Americans with Disabilities Act and the importance of making digital educational content accessible to all students affects the likelihood that faculty will make their content accessible. If you believe that as awareness increases, so does the likelihood they will make content accessible, then you're predicting a positive correlation. As one goes up, the other goes up. Then you might also state that as awareness goes down, the likelihood that they'll make things accessible also goes down. That's also a positive correlation because they're both going up or they're both going down. When both variables go in the same direction, it's a positive correlation. Now, if you believe increased awareness will lead to less application of accessibility techniques, you're predicting a negative correlation. So in the case of a negative correlation, if something increases and then it leads to the likelihood that something else will decrease, or the other way around. If something decreases, like access to school and libraries and various reading materials, then literacy rates, so if the access goes down, illiteracy rates go up, if that makes sense. That's a negative correlation, because as X goes up, Y goes down, or X is the independent variable going up, Y is the dependent variable, therefore going down, or the other way around. So in that same analogy, if greater access to public schools, reading, libraries, reading materials, etc., go up in a community, you might hypothesize then that illiteracy will go down. That's a negative correlation. As the independent variable rises, the dependent variable drops or decreases. So which statistical test do you use in correlations? You use Pearson's R typically. There's some other more complicated statistical tests, and you certainly can look those up in your stats or methods books. But to give you a general notion, if you're comparing the X and the Y as I've described here, you're looking for a positive or negative correlation. And most typically you'd use the Pearson's R. You may also use other correlational methods. Now let's summarize. Basic statistics depict information about variables. They do not tell you cause and effect. So when we do statistics, the reason we do them is so that we have a way to illustrate something. Statistics draw a picture. They just draw that picture with symbols that we oftentimes associate with math and other things rather than paintbrushes. So we don't necessarily see the illustrative factors of statistics, but in fact, that's what they're doing. That's why the news is so interesting to us when they will say 1/3 of all people, or 75% of all events in the United States, or 20% of the global warming effect, etc. We hear those statistics and we go, wow, what does that mean? That illustrates how many. We can picture that. That's what statistics are for. They're an art. They're just an art that use numbers and words to explain themselves. If you're looking at averages or means, you're simply applying statistics. So if you're doing qualitative data, but you want to still know, you still want to count how many times something occurs, and sort of describe on average it occurs this many times with men, and on average it occurs this many times with women, then you're doing statistics. You're doing averages or means. A mean can be meaningful, especially if analyzed alongside the median and the mode. With all of your research, you should at least look at the mean, median, and mode before you decide to discard the median and mode, because if there are outliers or extremes within your data set, the median and mode will tell you to look for them and consider more detailed and under-the-surface explanations. The likelihood that two variables occur more frequently together requires a look at relatedness, or applying the chi-square statistical tool. When we want to know if there's a correlational relationship between two variables, if as one moves, the other one also moves, either up or down, we're looking at Pearson's R, because we're looking for a positive or a negative correlation.